Okay, we're going to pick up where we left off last time, and that's with transport, or getting things from the inside of the cell to the outside of the cell, or from the outside of the cell to the inside of the cell. And this is called this membrane transport. So the first thing we need to realize when we do this is that the plasma membrane is selectively permeable. Is selectively permeable. So what this means is that certain things can go through the membrane without anything special, and some things cannot. Okay, so the things that can freely cross the membrane, so freely cross, are carbon dioxide, oxygen, okay, non-charged molecules, lipids, and water in most instances. Okay. Restricts, the membrane will restrict ions, okay, and large molecules. Okay. I want you to remember ions. So ions be like sodium, potassium, chloride, those things, anything that's got a charge on it. Okay, so selectively permeable. Certain things can go through, certain things can't. Okay. Now, transport itself comes in two main types. Okay, the first one is active. Okay. And what makes it active is that it requires energy. Directly in the form of ATP. Okay, you remember ATP is basically the human battery. Okay, so this is what we're going to start using ATP for. And then we have passive. Okay, and it does not require direct energy expenditure. Okay, so those are the transport, the two main categories of transport. So we're going to go through passive first. We're going to go through passive transport first. So passive transport. Okay. So there are two main categories inside of passive transport. One is diffusion, and the second is facilitated diffusion. Okay. So what this means is if you remember what diffusion is, you automatically know what facilitated diffusion is, because all the facilitated diffusion is, it means it has to have something it goes through. And that's it. Okay. So the guiding principle of diffusion, is this. Okay. A solute moves with its concentration gradient. All right. Okay. So this here is the term, the phrase that usually trips most people up when we're talking about this. Okay. So let's just say that I have a substance here. Okay, so we've got 10 particles of, I don't care what, it doesn't matter what it is. And I put it in a container this big. This big. And this is to say that it's some kind of something you can smell or something like that. Okay, what you have to understand is in this container, you have these other substances, air molecules, and they're all just bumping around each other. They're hitting each other. They're moving back and forth, you know, and they have a natural energy itself. Okay, there's an energy itself. And what's going to happen with those air molecules, okay, all that stuff that's already floating in the air, is they're going to hit that substance, that red substance, that smell substance you can do. And what it's going to do is it's going to start pushing them. And they're going to get hit more and more and more and more, and they're going to start getting pushed farther and farther and farther apart. So eventually what we're going to see is in this container, excuse me, they're going to spread out. They're going to spread out. They tend to spread out. It is diffused. It is diffused. All diffusion is it wants to go from a higher concentration gradient, high, and it wants to roll to a low concentration gradient. Okay, so the general principles of this are that all molecules are in motion. Okay, and it's this motion that provides the energy for diffusion. Diffusion does require energy. Okay, I don't want anybody to ever say that, oh, there's no energy in diffusion. Yeah, there's a lot of energy in diffusion, but it's not direct. Okay, it's pulling the energy from just its general surroundings. Okay, so now this random motion that we have from this, and what's going to do is basically causes mixing. The random motion causes mixing and will cause things to mix. Okay, and in diffusion, the particles always move from an area of high concentration to low. Okay, unless it's forced to do something else. Okay, and normally it is just a passive process. So another example, let's say we have a room. Let's say we have a large room, a large classroom. Okay, and how you'll be in class is you'll have a table here, there'll be a table over here, there'll be a table over here, and then you have the instructor bench was up here like this. And we have all these students. The students are around the tables, sitting around their tables. Yep. Around the table like that. And let's just say that I have a candle. It's called pine scented candle. Pine scented. Okay. And I light this pine scented candle. I light it. Okay. Now every one of you knows exactly what is going to happen with this. Okay. As I light this, what's going to happen is I'm going to start releasing the aromatics from this pine scented candle. They're going to go up. Okay. The people who are closest to the candle are going to smell it first. Now the question you have to answer is why? Sorry, how? How are they going to smell it first? Well, it's particulate. It's particulate. When you burn a candle, you're releasing these particulate substances, these microscopic particulate substances, into the air. Okay. Remember, the air is not just empty space. Okay. There's a lot of molecules that are floating around inside of the air. And those particles that the candle is releasing as it's burned are going to start getting hit by the oxygen molecules and the water molecules in the air and the bacteria and stuff that are just floating around in the air. Okay? And they're going to start getting spread apart. So eventually what we're going to see is we're actually going to see there's going to be a trail of smell that will eventually spread throughout the whole classroom. Okay? And the reason it's going to spread out is because the candle is an area of high concentration of these particles. And as they're released into the environment, they're going to start to spread out into an area where there are no particles. It's going from an area of high concentration, which is the candle, to an area of low concentration, which is the room. Okay. The nice side effect of this is pine scented candles smell pretty good, so everybody will smell them. Okay. Another example of diffusion is one that you have most likely seen. Is if you have a glass of water, let's say we fill this glass up with water, okay, and let's say you put a cube of table salt. You put a cube of sodium chloride inside of that. And you just leave it alone. Let's just say you just leave it alone, do nothing to it. What is eventually going to happen to the sodium chloride? It's going to dissolve. It is going to dissolve. And the reason it dissolves is because of diffusion. Okay? Right here, this sodium chloride being in this block, this is a high concentration, increased concentration. Okay? The water around it, this is low concentration. So what the sodium chloride is going to do, it's not that it wants to do, what it is going to do, based on the rules of diffusion, is we are going to move from that area of high concentration, and the sodium chloride will be dispersed out into the areas of low concentration, to where eventually what we're going to see is we're going to see this cup again. It's still going to have water in it. There's going to be water in it. But inside of it, we're going to have the sodium chloride the sodium chloride atoms scattered all around, and you can't see them. The important takeaway from this is we no longer have a cube of sodium chloride. It's now dispersed in the fluid, and that is diffusion. Okay, so what you have to remember about diffusion is it is the movement of a solute. Okay, and it always goes from an area of high concentration to an area of low concentration. Okay, and it does not require direct energy expenditure. Okay, the energy for diffusion to occur comes from the environment. Okay, so what spreads those molecules out is the molecules hitting the solutes. That's where that energy gets. So you hit a molecule, it's gonna move away. It's gonna get hit again. It's gonna spread out farther until it's very equally distributed. Okay, and when it is equally distributed, it is called equilibrium. It is at equilibrium. Okay, so that's diffusion. Now, what will affect the rate of diffusion? Rates of diffusion. Okay. What will affect them? What will make things speed up and what will make things slow down? Okay. Number one, the distance. The distance a solute has to travel. Okay. So if it's got to travel a shorter distance, the diffusion is much faster. If it's got to travel a larger distance, the diffusion is much slower. I mean, that's just common sense. Okay. Let's say that you have a car and you can only drive 30 miles per hour. Okay. If you're going to just go a mile, that's going to be a shorter time to get there. Whereas if you had to travel 15 miles, it would take you much longer to get there going at 30 miles per hour. That's just how it is. Okay. The next thing that will affect the rate of diffusion is the molecular size. Okay. Now, the larger the solute, the slower it moves. So if you have a slow-moving solute, it's going to move slowly. And also this means that if I have a large solute, it's going to take more collisions with air molecules in order to spread it out. So molecular size, the larger equals slower diffusion. All right. And then we have the temperature. Okay. Now we've talked about temperature before. And temperature, with increased temperature, that means the molecules are moving faster. Okay. So if let's just say for the scented candle, let's say that it's 50 degrees versus like 90 degrees inside of a room. At 50 degrees, the total velocity of the air molecules is lower than the velocity of the air molecules as it's being warmer. Now, if you hit something with a higher velocity, that means you're going to hit it harder. And because the molecules are moving faster, it's going to get hit more frequently. So temperature will increase the rates of diffusion. So increase temp equals increase diffusion. Okay, so increased temperature will increase the rates of diffusion itself. Okay, concentration gradient. Okay, now the concentration gradient is this. Let's just say, I have a block of sodium and a glass of water that has that's green water, don't want that. That has nothing else in it. Okay, that's going to dissolve very quickly. It's going to dissolve very quickly because it is an incredibly high concentration gradient. Okay, we've got a very concentrated sodium chloride with going into a solution that has no sodium chloride. So that's going to be a very high. Now, however, if I take the same sodium chloride, I take this same sodium chloride, I put NaCl so you know what we're talking about. NaCl. If I put this same block of sodium chloride in water that has sodium chloride inside of it, this is NaCl as well, I have less of a concentration gradient. It's less of a concentration gradient. So you can say that the sodium, let's just say here sodium is 100 on this one, and the sodium inside of the fluid is, let's say, 0. That means our concentration gradient is basically 100. It's 100% concentration gradient. So the sodium chloride is going to quickly disperse out. Now let's say in this, so we'll call this A. And we'll call this B. And let's say in B, in picture B, let's say the sodium chloride, the block is 100, and let's say the sodium chloride inside of the water already, and let's just say it's 50. Okay, so the concentration gradient of A is 100. 100 minus 0 is 0. And the concentration gradient of B is 100 minus 50, which is 50. So that means the higher the concentration gradient, 100, it's actually going to dissolve faster. Whereas if I have a lower concentration gradient, and like in example B, it's going to dissolve much slower. Okay, now, will it dissolve? It depends. Okay. You can supersaturate a thing, but it will start to dissolve. Okay, just because there's sodium chloride present in the water in sample B doesn't mean that it won't dissolve. It still will dissolve in order to equalize out all of those concentrations Okay, it will. So concentration gradient. The greater the concentration gradient, I'm going to call that Cg, equals increased diffusion. Okay. And then finally, electrical forces. Okay, electrical forces. Now, this is one where you actually have to visualize this one a little bit more. Okay, let's just say that I have a glass of water. And I put a charged ion in there. Let's just call it ion X with a positive charge on it. Okay, I can't put sodium in there because if you put sodium in water, it explodes. So I'm just going to say just any ion with a positive charge. Now, let's just say I have an electrode. Let's just say I put an electrode in here. Okay, and this electrode, what it's going to do is it's going to make the water positively charged. Okay, now since our solution, our solute X has a positive charge and the water has a positive charge, what that's going to do is it's actually going to slow down the diffusion. Because remember, like charges repel like charges, so it's going to resist it. Will it diffuse? Yes, it will, because there's two things happening right here. Okay, you got the molecular, you got the concentration gradient, which will happen. Okay, that's going to happen, but then you have the electrostatic forces, which are just going to slow it down. So it still will dissolve. It'll just do it at a much slower rate. Okay, so now let's just imagine. Okay, so this is sample A. Okay, and so we're going to go to B over here. We're going to use the same cup, and we're going to have the same element X with a positive charge on it. Okay. And we're going to have the same electrode in it. And we're going to put some water in here. But instead of making it a positive charge, we're going to give the water a negative charge. Okay. Now, since positive and negatives, they like to hook up. This is going to actually increase the diffusion. So what you're going to have is you're going to have the concentration gradient effect that's going to make it want to diffuse. Now you're going to have the electrical effect, which is going to want to make it diffuse faster. Okay, so electrical forces. Like charges will repel. So like charges will slow down. Okay. Whereas opposite will increase diffusion. Okay. So like charges, we're going to slow diffusion. Opposite charges are going to increase diffusion. Okay. So those are the principles of diffusion. Diffusion is really not that hard. I think a lot of students, what they do is that they hear this word and it's a scientific word and they make it difficult. Nope. So if you want to be crude, just think of a fart in a car. Somebody farts in a car, everybody smells it. You know, the reason that is because it's diffusing through the air. Okay, and in that case, the one who smelt it dealt it because it's going to come up to their nose before it goes into anybody else's. All right, so that's diffusion. So if you think of passing gas in the car, you got the general principles of diffusion. Okay, so now we're going to look at facilitated diffusion. Now you don't have to just like go super complex, but all the facilitated diffusion is it has to have help getting across. So here's our plasma membrane. So we're going to draw our plasma membrane right here. And you remember, inside of our plasma membrane, we have these integral proteins, right? Okay. These integral proteins. And remember, some things just can't cross the plasma membrane. Some things just can't cross the plasma membrane. Okay. So let's just say that we have just a bunch of sodium that's floating around here. And the sodium concentration on the outside of the cell, we already know, is greater than it is on the inside of the cell. So sodium is going to have a propensity to want to get into the cell, to diffuse itself out. Now, don't hold this as truth. I'm just using this as an example because it's a lot more complex than this in reality, and we're going to go over that. So sodium, if it tries to cross through the plasma membrane itself, will just bounce off. This is going to bounce off the plasma membrane. However, if you have a sodium channel, okay, the sodium can be carried through. All the other rules of diffusion apply. Yep. Okay, all the other rules of diffusion apply to facilitate diffusion. You just have to have something help you through. Okay, and this is called channel mediated diffusion, but it is still facilitated diffusion. Now, the things that usually have problems with this are your sodiums, your ions usually have to do this way, and your sugars. A lot of sugars have to go through this way. Okay, so I think we're gonna leave it there. I think we're good. I think we're good on the diffusion here. So next we'll talk about osmosis in the next lecture, and then we will go into the active transport and the co-transport systems. But that's enough for now.